And I'd like to welcome everyone to this week's edition of the HoloTube seminar series. Today we are very happy to welcome Amos Yarom, and he's going to talk us about his recent work with Sebastian Weber on stochastic gravity and turbulence. The floor is yours.
Okay, thanks a lot. Thanks for the invitation. Before I start, I don't mind if you keep your cameras closed, but if you ask a question, please turn on the camera so I can see who I'm talking to. I'm going to talk about some very recent work I did with Sebastian, who's currently a postdoc at the Technion. He's going to move to University of Washington soon. And this is work about holographic turbulence, essentially. Before I go into the details of what exactly we did and why we did it, let me start with just reviewing briefly what it is that we know and don't know about turbulent flow, and how we expect, and what exactly is this program about? How do we expect holography to help us with it? So I wrote down here the incompressible Navier-Stokes equations. I'm sure you've seen them at one point or another. These equations describe fluid flow to a good approximation. And as you know, they can describe very robust phenomena, many scales. Once the fluid description is good, then these equations are going to be good for describing the appropriate physics. And I wanted to talk today in particular about turbulent flow. So when we see flow that's turbulent, we sort of know that we're seeing something turbulent. But as physicists, we want to somehow quantify turbulence, somehow say this is turbulent behavior, this is not turbulent behavior. We need some number or some parameter or some function that we can use to define turbulence. And well, one thing that we can say about whether or not turbulence appears is associated with a certain parameter called the Reynolds number, which once it's big, then we expect turbulence to appear. So it turns out that these Navier-Stokes equations have one dimensionless parameter. It's called the Reynolds number. It's a typical velocity scale times a typical length scale divided by the viscosity. And if that number is very big, then we should expect turbulent behavior. So the Reynolds number is something that characterizes when we expect to see it. What Kolmogorov did was to actually quantify turbulence itself. So what Kolmogorov said was that if we add a random driving force to the Navier-Stokes equations, and by that I mean some sort of force that averages to zero, once we do that, then these correlation functions of the velocity field will scale like the distance to an appropriate power. So this is Kolmogorov's theory of turbulence, and it quantifies turbulence. It says that if you measure this quantity and it scales in this way, then it means that the behavior is turbulent. So this is the theoretical construction, and now we can go ahead and check whether it's correct. So if we take n equals 2, then we can relate this 2-point function to the energy density. So in incompressible flow, the mass per unit volume rho here is a constant. So the energy density is really associated with just the velocity squared. And using this relation for n equals 2, one can show that the energy density should scale like the length scale to a certain power. And usually this is written in Fourier space. The energy density in Fourier space is the averaged energy density in Fourier space is going to scale like the momentum to some power. This is the -5/3 law. And one can carry out an experiment or an actual experiment or a numerical simulation. And what you see in this plot is exactly the Fourier transform of the energy density, what's called the energy power spectrum. So in the paper that I'm citing, they used E instead of epsilon hat. The horizontal axis is the momentum. And you can see that there's a range of momenta here, 2 decades worth, where the energy power spectrum, epsilon hat, scales very close to k to the minus 5/3. So in this case, when we see this, we say the fluid is exhibiting turbulent behavior. For n equals 3, it's the same story. We get something that scales like the distance to the power of 1. And again, there are numerical simulations and experiments which show that this behavior actually matches theory. So F3 is just this third power of the average of the third power of these velocity correlations. You divide it by R, you expect to get a constant. And indeed, there's a range of scales where you get this constant. It turns out that for higher powers of n, the story doesn't quite work the same way. So experiment and theory deviate for larger powers of n, of this correlation function. And this goes under the name of intermittency for various reasons. But the punchline is that we really don't understand these correlation functions very well. It's something that's still in the open, and I don't think there's agreement in the community as to what exactly is the mechanism that'll give us the correct experimental results. So this is an open problem. It's really a problem of quantifying turbulence. And like I said, there are various techniques one can try to use to understand turbulent behavior. Coming from the point of view of looking at this from the point of view of our community, we can try and use holography to maybe make some statement about how exactly these these correlation functions should behave. By that, what I mean is, what we can try to do is try to look for some sort of holographic dual of turbulent behavior. Once we have that, maybe we can identify some sort of geometrical structure associated with black holes in ADS space that'll encompass or incorporate this power law behavior of correlation functions. And if we manage to identify what exactly is the geometric quantity that's associated with these correlation functions, which are assumed to be universal, then maybe we can also predict it using more highbrow tools of differential geometry. So this is what this program is about. And what we did is a certain step in attempting to understand turbulent behavior via ADS-CFT. Questions so far? Okay.
Yeah, actually. Hi, Amos.
Hi.
Sorry, I had some troubles with my camera. Now it's better.
It's okay.
I'm not sure if I missed it already in your talk, but these scaling laws, they have obviously a UV and an IR cutoff where they stop being valid.
Yes.
Is there a universal reason why there are these cutoffs, or is this case by case? What? No.
So yeah. Okay. So what I let me give you. Well, I wanted to say a short answer and a long answer, but I think they're both going to be long. So this is an excellent question. So in these simulations, what one does is insert like I said, a random driving force, and that random driving force is essentially an oscillatory force at some scale. So if we're working in 3+1 dimensions, the range where you'll see this scaling law is above this driving scale, above the scale where the force enters, and it'll end at the dissipation scale. So at the scale related to the viscosity. Okay, so that's where the inertial range will be. And I don't know, so it will depend on these two parameters. Now, what I'm going to show you is a 2+1 dimensional setup, and there things are a little more complicated, and I wasn't planning on really explaining it. At the end of the day, what you get in 2+1 dimensions is that for scales lower than the forcing scale, you get the -5/3 law, all the way up to 0 momentum.
So there's no IR cutoff.
There's no IR cutoff, and well, so what happens, so the reason you get this inertial range is that in 3+1 dimensions is that you're pumping energy into the system. And then this energy sort of goes into higher and higher momentum modes until it dissipates at the dissipation scale. So you reach some sort of steady state where you pump energy in and it goes out somewhere. In 2+1 dimensions, because it works the other way, it'll come in through your driving scale, and then it'll go to lower momentum modes. And what will happen is that if there's nothing to dissipate it, it'll just blow up eventually. So what people do is they usually introduce by hand an extra, what they call large scale friction, which essentially just, you know, it takes away these very low momentum modes.
Okay,
So
okay.
it's sort of it's something that it's an extra friction that you introduce by hand.
Okay, thanks. Thank you.
So you are talking about classical turbulence instead of quantum turbulence, am I right?
Yeah, this is all classical.
Okay, thank you.
Any more questions?
One more question.
Yeah.
When we were talking about experimental results, are those numerical studies or?
What I showed is numerical. There are some
Okay.
experimental results which I didn't show them, but there are experimental results which look the same.
Okay, it looks the same. Good. Thank you.
Amos, I have also a question.
Yeah.
The absence of, let's say, UV cutoff, is it to say that it is equivalent to have a cascade, an inverse Richardson cascade?
No, so no. What happens in 2 dimensions is that you actually have a -5/3 law at momentum smaller than the driving scale, and you have a -3, I think, law at larger momentum. So you have two different cascades in 2+1 dimension. One is called an entropy cascade, and the other is an energy cascade. In our setup, it's harder to get the other cascade, so we're just going to see the -5/3 one, which is why I'm focusing on it. So it's really very subtle. I mean, the 2+1 versus 3+1 is actually very different. And it's kind of, well, I shouldn't say accidental, but it's at first naively you'd say 2+1 and 3+1 are the same. You get a -5/3 law, and then when you actually see the details, you say, oh, they can't possibly be the same, but they turn out to be the same at the end anyway, except that they're they occur at lower momentum instead of higher momentum. But it's really very different. It's just that I don't really have time to go through, you know, a finer description of turbulence. I just wanted sort of a very broad overview.
Thanks.
Okay, so how are we going to get turbulence from a holographic point of view? Well, I think most of you have already seen these things. So the ground state of our field theory is going to be dual to an asymptotically ADS space. If we have a black hole, we're going to get a thermal state. Usually, we want to look at Poincare patch of our space, because we want to talk about field theory in a flat background. And if we want to look at fluid dynamics, then we sort of look for black hole solutions which are not uniform, but vary slowly in space and time. And those slow variations correspond to a derivative expansion in the boundary theory. Now, so this fluid description is this dual fluid description is of dual fluid description relating black holes which are close to equilibrium to fluid dynamics is something that I hope you know. I'm not going to spend too much time on. Once we have this description, what we can try to do is to actually solve the equations and see whether we can see turbulent behavior. So there's a very particular paper from the MIT group that came out in 2013. And what they did was they said, okay, let's just try to start up with t equals 0. We'll start off with some configuration which is not in equilibrium. It's an out of equilibrium black hole. From the dual point of view, it corresponds to an a thermal state which is not uniform. And then they just let that thing evolve in time. And you see pictures of the vorticity which show this evolution. Now, of course, there's no driving or anything. So what's going to happen is that you excite the black hole, and it's going to do something, and eventually it's going to settle down to a translation invariant state. And what this means is that we have some fluid. We start off at t equals 0 with some excited state. It's going to do whatever it does, and at late times, it's just going to settle down and become and go back to thermal equilibrium. So this is what they observed. But what they could do is they could take a snapshot at an appropriate time of the energy power spectrum. And what this group found was that there was a -5/3 law in some range of momentum. And this should remind you of the -5/3 law that we expect to see. So this is kind of neat, but you should ask some sort of questions about this result. First thing that you can ask is whether we're seeing here relativistic turbulence or non-relativistic turbulence. Of course, we can actually check whether the velocities are large or small, and it turns out that the velocities here are small. So this is really non-relativistic turbulence. So we can use what we know about the power spectrum of non-relativistic turbulence, which is what the authors did, to see whether or not Kolmogorov scaling works here. Let me mention that relativistic turbulence is really problematic, and there I think almost zero works on the subject. And the problem is that when you want a theory to be relativistic, you need V over C to be of order 1. If V over C is 1/3 or 1/2, then relativistic corrections to a non-relativistic theory are going to go like V over C to the power of 4. So it's going to be a small number unless V over C is of order 1. Now, if V over C is of order 1, then we're talking about supersonic flow. And then there's this whole issue of shock waves and such that come into play. And turbulence becomes much more complicated, and it's not even clear it's universal. So relativistic turbulence is something that I personally would like to understand. I'm not going to say anything about it in this talk. Everything we're going to do is at small velocities. So we're going to make sure that our velocities are small enough so that the non-relativistic approximation is a good one. Another thing that we should obviously ask is what exactly are we seeing here? There's no driving force. This random driving force that Kolmogorov introduced in order to get his cascade doesn't appear. And what we're really seeing here is something called decaying turbulence instead of steady state turbulence. When you have the driving force, you get steady state turbulence, which is what this plot depicts. If you don't have this driving force, then you get decaying turbulence, which means that you're exciting the system, you're letting it decay. You hope that turbulent is some sort of fixed point so that the flow will go next to turbulent solutions for long enough time so that you'll be able to see it. In practice, decaying turbulence is difficult to analyze. You can get various power law behaviors depending on boundary conditions and exactly what you put into the system. It depends at what time you take your snapshot of the energy power spectrum. So this is really not something that's as well understood as steady state turbulence, where you have a non-zero driving force. So what we want to do, and this is what the work I'm going to talk about is to introduce a non-zero random driving force in order to get steady state turbulent behavior. Since we want to do this in a holographic context, the question is, how do we introduce in a of course, we can always take the Einstein equations and introduce by hand some random force and just say this is what it is. But what we want to do is do it in some self-consistent way within the standard rules of holography. So that's sort of what our work is about. So there's this duality between black holes and fluids. What we could do from the fluid perspective, whatever we do in gravity, it would transfer to a fluid perspective. So if you want to introduce in some way a random force within the context of field theory without introducing it by hand, we need to somehow think about incorporating it in terms of an action principle or in terms of some microscopic description. And the way we decided to go about it was to just place our theory on a manifold where the metric in the field theory is a random variable with an average, which is just the Minkowski metric. So what this means is that we have a field theory that's placed on a background metric. The background metric just changes randomly in space and time in such a way that its average is just flat space. This means that in gravity, we have to introduce boundary conditions for the metric such that the boundary value of the metric is a random variable with this average. The reason this is helpful is that if we write the metric as the average plus some random variable, and we also write the energy momentum tensor as the energy momentum tensor that comes from Minkowski space plus some correction, then the conservation equation can be written in this form. So F is whatever is not included in the divergence of the energy momentum tensor in flat space. And then we get a non-conservation equation for the energy momentum tensor, which takes this form, where F is composed of components of the energy momentum tensor plus multiplied by the fluctuating part of the metric. So what we get here is if we think of the energy momentum tensor as a flat space one, we get a non-conservation equation of the type that we're looking for. So this should map in a gravity setup to in theory where the boundary value of the metric, like I said, is random. I should say this idea has been around. The group in India worked out some of the equations on this side and on this side for when the metric fluctuations are small. This has also been worked to some extent in the large D limit. But the main problem with works that have been done up until now is that this equation here is a stochastic differential equation. What that means is that if part of the equation contains a random variable, it means that whatever other terms we have in the equation are also random variables. So the energy momentum tensor is now a random variable. If it's an operator, it's a random valued operator. And this is a differential equation for random variables, and that requires some work in order to solve. It's not a standard differential equation. So since I think not everyone here is probably familiar with how stochastic differential equations work and what exactly are the subtleties with them, let me just make an aside on stochastic differential equations. So let's suppose that Q is some random variable that we're trying to solve for. Q dot is the time derivative of Q, and it satisfies this first order differential equation. So G is some real function of Q, say Q squared. H is another real function of Q. And Xi is a random variable, an external random variable. Usually, one chooses white noise for Xi, which just means that its average is 0, and its autocorrelation function is some number times a delta function. This can be achieved if Xi is drawn from a normal distribution at each point in time. So this is called a stochastic differential equation. And what one does is try to find what is the distribution of Q given the distribution of Xi. So the first step in solving this is to just rewrite it in integral form. And here there's a subtlety that we're going to need to address. And the subtlety has to do with integrating random variables. So this integral of G, we can write it, we know that we can write it as the area under the curve G of Q. And we can approximate this area by looking at rectangles of appropriate height and computing these for rectangles of smaller and smaller width. And we know that at the end of the day, we're going to get an expression which we call the integral of G. Now, it doesn't matter how exactly we define these rectangles. We can take a rectangle whose height is the average between the two endpoints of its width, or the left side or the right side. We always get the same result. So this is true for general functions, but if we integrate over distributions like this, we're going to run into some problems, which is what I want to talk about. So let's suppose we define this integral as this limit. Again, we look at these rectangles, and I'm going to leave the integral over Xi to be an integral because Xi is really a distribution, so it's really only defined under the integral. So I'm going to integrate Xi along these intervals delta t, and I'm going to approximate this function h in the usual way. So I can do it this way, I can do it this way. What I want to show you is that you're going to get different results depending on how you compute it. So let's look at the left-hand side, and let's try to compute the average of this expression. So the average is going to be given by the average of h times Xi over this interval between delta t and between n times delta t and n plus 1 times delta t. Xi is going to be in this range. It's some random variable that's fluctuating in this range. And h of q, we're evaluating it at the beginning of this range. Often, because of the differential equation we start with, q is not going to know anything about the future of anything that happens in the future of its argument. So under some assumptions about causality, h and Xi are not going to be correlated. The average of h times Xi is going to be 0 if Xi is to the future of h of q. Okay, so in this case, we're going to get 0. On the other hand, if we look at the other version of this integral, then, well, you see that h is to the future of Xi, and therefore, generically, this is going to be non-zero. And this is sort of, I wouldn't say an issue, it's a feature of stochastic differential equations. We're used to regular, ordinary, or partial differential equations or ordinary differential equations. We write down the equation, we write down the initial condition, and that gives a unique solution. In stochastic differential equations, we write down the equation, we write down the initial condition. We also need to say what is the integration rule that we're going to use. So it's some extra information that we need when we write down stochastic differential equations. Now, luckily, in our case, we're free to choose what sort of integration scheme we want, because our metric is an external source, and we just have to specify what sort of stochastic variable is it. So there are two standard integration schemes. One is called the Ito integration scheme, where essentially h is always evaluated to the left of psi. And there's something called the Stratonovich integration scheme, where h is some averaged value. The Ito scheme is very useful for mathematicians. It has nice properties. You can prove a lot of theorems using it. The Stratonovich scheme is actually more useful in physical setups. We played around with both. We found that the Ito scheme gave us some non-physical results. Energy density started going down, even though there was driving, things like this. So after playing around with it a little bit, we decided to use the Stratonovich scheme, which, like I said, is usually more useful for physical problems. So this is one thing we had to choose. Now, once we choose a scheme, we can actually solve this equation. So, for example, if we take g to be just a constant and h to be a constant, then one can just solve this equation directly, and this is what the solution looks like. At t equals 0, q of t is q0, and when t is not 0, it's a distribution. It's a random variable, and we can compute its average and its correlation function once we know the average and correlation function of psi. Okay, so this is a solution to a stochastic differential equation. Like I said, the solution, what we get is a random variable, not just a regular variable. Usually, we can solve it analytically, and then if we really want to look for a solution, we have to solve it numerically. So there's an equivalent of Euler evolution, and you get an expression which looks like this. What's funny about stochastic differential equations is that you get square root of delta t all over the place, and this has to do with the fact that psi squared goes like a delta function. And this can be continued to higher order. I'm not going to go into details. All I wanted to show you is that it can be done, and there's an actual scheme for solving these equations numerically. Okay, so going back to this setup, this equation is now well defined, and we can try and actually solve. So here's what we want to do. We want to solve the Einstein equations in the presence of a cosmological constant. We want the system to be in thermal equilibrium at early times, but at t greater than 0, we want to have the metric start, the boundary value of the metric become a random variable. So it's going to oscillate around the Minkowski metric. So we could write something of this form.
Amos, sorry, can I ask you a question?
Yeah.
What's the reason why you're looking at this problem in 2+1 dimensions and not 3+1?
Because it's much easier to solve it numerically.
Okay, you mean solving the Einstein's equations with this boundary condition?
Yes, yeah, it's just it's an extra dimension. Even this was a little bit hard. Okay. But there's no, apart from numerical, apart from numerical issues, there's no reason.
Okay, thanks.
Okay. So this is what we'd like to use. But you quickly run into a problem if you do this. And the problem is that the differential equations that you get are going to be polynomial in this variable psi, or in this sort of random part of the metric. And that's a problem. That's a problem because then, once you average over your equations, you're going to get things that are not well defined. Okay, so this is just not, at least in terms of holography, we don't get a well-defined set of equations if we put in a boundary value for the metric, which takes this particular form. So what we need is some distribution where this delta function is smoothed out. And what we chose to do was to use a random variable q here, which satisfies an equation of the type I described before, where now psi is some white noise of this type. So it's what we had before, except that now instead of dependence on t, there's a dependence on t and x of all these variables, but the x dependence is smooth, and the correlation function in time is a delta function. So q behaves nicely, psi doesn't, but it's q that's going to appear in the equations in such a way that that will only have psi and its powers appearing. D, we're going to choose D. Was there a question?
Yeah. So couldn't you then move the deterministic part of Q to the 1 and have again Psi there in the bracket?
No, it's not a matter of deterministic part of Q. Q is going to be some sort of, I mean, we're gonna solve this equation saying that at t equals 0, Q is 0. I'm not sure what you mean by the deterministic part. So Q.
Well, you showed the solution for.
Yeah, the solution has an exponential decay of the initial value, so we just choose that to be 0. So the initial value of Q is 0. Q at t equals 0.
Oh, okay, thanks.
Any more questions? Okay, and we choose D to be such that in momentum space, it's sort of driving the system homogeneously with some scale kf, which is what one usually does in turbulent flow. Now we didn't quite do this. The problem with this is that you can get a metric. You can change the signature of the metric if Q fluctuates too much. So there are several ways to resolve this. What we did was just add to it a number sort of large enough so that statistically speaking, we won't run into these types of issues. But you could also put in some exponent of Q or little q or something like that. It'll solve it all the same. Okay. So this is what we used. And once we have this, then you use the standard rules of holography to compute the energy momentum tensor from the metric. What you need to do in this case is run this many times, because Q is a random variable. If we just do one run, then there's no randomness there. We're just choosing, some particular values of Q. It'll just be like a deterministic system where Q takes a particular value. If somebody else runs the same simulation with the same values of Q that I chose randomly, they'll get the same result. There's nothing random in it. What we need to do is run this many times, compute the dual energy momentum tensor many times, and then take the average. That would give us the average energy momentum tensor that we're looking for. So this is what we did. In practice, you obviously need to solve this numerically, and we put the whole system on a grid, and we used a rather small grid because at this point, at least, we're only interested in getting this scaling region, this power law for K. Obviously, you'll see we're going to want to improve this in the future. We're using periodic boundary conditions, so this is just useful because it's on a torus. And this is the standard thing. If you solve the equations at the right order, you get ordinary stochastic differential equations at every point on the grid. This is pretty much standard by now.
Sorry, Amos, one question. Maybe I'm missing the point here. So if you have to run this many times, So naively, this sounds to me, but I must be wrong. It sounds like solving the usual problem with a perfectly deterministic and well-defined boundary metric. Many times where you simply, every time you solve the problem, you change by hand that boundary metric in such a way that at the end, you're sampling over some distribution of boundary metrics. And at the end of the day, you take the average over the final results. But in this way, you would never be solving a stochastic differential equation.
Well, no, we cannot solve a stochastic. So, right, when you solve numerically a stochastic, I'll answer what I think you're asking. If I didn't answer, correct me. But suppose we have some stochastic differential equation, and now we want to solve it numerically. So obviously, when we solve it numerically, we cannot find the distribution of our variable q. What we do is we say, let's just have 1,000 runs. And now we can compute the average of q, the average of q squared, the average of q cubed, the average of q to the fourth, and we just have a numerical evaluation of various moments of q. So when you solve things numerically, at least as far as I know, you can't actually get this distribution, you just get all possible moments. So it's the same here. I don't know if that answers your question.
Yeah, I think to some extent, yeah, I need to think about it, thanks. Yeah.
Okay. Any more questions? Okay, so this is what we did. Let me show you what it looks like. So what I'm plotting here is the 0, 1 component of the energy momentum tensor, of the boundary energy momentum tensor. The axes are the spatial directions. This is a snapshot in time. And the units here are units of the initial temperature. So remember, the whole thing was in thermal equilibrium at T smaller than 0. So I'm using that temperature as my inverse length scale, and everything here is in units of that inverse temperature. And again, this is not, I didn't average here. What we're seeing here is just a single run, a snapshot of a single run. So you see there's some scale here in this plot, in this fluid, there's some scale. This scale is really just the driving scale. So remember, the whole thing is being driven with some oscillatory force, which has a scale. And what we're seeing here is just that scale. So visually looking at real space, we can't really see any interesting features. All we're seeing is the driving scale. What would be useful is to do a Fourier transform and see what the Fourier modes of the energy momentum tensor are doing. So this is what I've plotted here. So what you're seeing is the following. So L is just the length scale of space. F are the Fourier modes. So since we're on a torus, momentum is discrete. So this is really a Fourier series. F are essentially our Fourier modes. And here, what I've plotted is the absolute value of the Fourier modes. And N are the values of the momenta up to factors of 2 pi over L. So this is what the previous plot looks like in Fourier space. This ring here is just the region where we're driving. So wherever we're driving, it sort of dominates the entire spectrum. In order to understand a little better what's going on here, what we can do is treat these integers n as continuous, meaning we extrapolate the Fourier modes to some sort of smooth function, and then integrate over all the angular variables. So we're averaging over the angular variable to obtain sort of the behavior along the radial direction. So this is what we're doing in practice. And when we plot it, we see something like this. So this dashed red line is the driving scale. And the blue line is sort of the average of f. If I average over circles of constant n, I'm going to get these values here. So like I said, this is for a single run. If we ensemble average over a little less than 40 runs, we get something like this. And since this is almost a steady state, we can also average over time to get something that is a little more stable, and it's what you see in pink. So the driving force, the size of the scale of the driving force goes down. This is because it's a random force. So once we average enough, it should go down to be very low. And the question is whether there is some sort of behavior at momenta that are below the driving scale. This is what we're after. So first thing we'd want to do is, check, get some notion of velocity from our solution and check whether our velocities are non-relativistic. And once we have that, then we can attempt to compute the power spectrum and see what it does. So this is what we'd like to check. What we do is we just define a Landau frame velocity field. It's the eigenvalue of the energy momentum tensor with a negative, it's eigenvector of the energy momentum tensor with a negative eigenvalue. And from that, we can define a velocity field. We can check that the velocity field is non-relativistic. You can see the velocity field, the maximum value of the velocity field at each point in time as a function of time is pretty low. And so we can try to evaluate the energy power spectrum using this method, the non-relativistic energy power spectrum using this method. And this is what we get. So the vertical axis is the energy power spectrum. The horizontal axis is the momentum. And we plotted for each time, we plotted the value of the energy power spectrum. So at early times, we get a behavior, you see that's very close to zero. It starts off at zero. And then as time evolves, we asymptote to this power law behavior, which is what's predicted by Kolmogorov. And we did a fit for exactly this range of momenta, and it was very close to 5/3. Certainly within our errors, it was 5/3. I chopped off the driving scale. Usually what happens is one can wait long enough until this region where you see the power law behavior is just above the driving scale. We had some issues with that I'll hope will resolve in the future. But here we do see the Kolmogorov scaling. As we do see an asymptote, how the energy power spectrum asymptotes to minus 5/3 behavior. So this is one of our main results. What we're demonstrating here is that by placing the theory on a random metric, we can generate, it serves as a random driving force which generates steady state turbulence in the sense that we're used to in non-relativistic systems. Now, what we'd like to do is understand how all this maps to the bulk. So here's a picture of the 0,1 component of the energy momentum tensor in the bulk. These are the spatial x1 and x2 are the spatial directions. Rho is the radial direction of ADS. Rho equals 0 is the boundary. And as rho increases, we go further and further into the bulk. Rho equals 1 is where the original apparent horizon was, t smaller than 0. At t bigger than 0, we can it's very difficult to compute the event horizon, but there's an apparent horizon that's within rho equals 1 up to maybe 10%. So this is what the 0,1 component of the metric looks like. Again, it's not very, so obviously it's dominated by the driving force. Again, it's useful to go to momentum space to understand what exactly it's doing. So what we did was for each of these slices, we went to Fourier space, and then again, we angle averaged. So what you see here in each of these curves is the value of the angular averaged 0, 1 component of the energy momentum tensor as a function of the radial direction. And what you're seeing is it really, it's whatever behavior it had close to the boundary, it has the same type of behavior, except that it's warped in the sense that the fluctuations increase. And this is kind of like an ADS version of inflation. As we go deeper into the bulk, the warp factor, the 1/ρ² warp factor, it just increases whatever small perturbations we had near the boundary. Okay, so the 0, 1 component of the energy momentum tensor is going to be associated with the behavior close to the boundary. The 0, 1 component of the energy momentum tensor of the dual theory is going to be related to the value of the 0, 1 component of the metric near the boundary. And as we go deeper into the bulk, we just sort of enhance this behavior. So at the event horizon, we expect to see some image of the behavior of the energy momentum tensor of the boundary theory. So to understand this a little better, what we did was we computed the apparent horizon. Like I said, the apparent horizon is within 10% of the apparent horizon at t smaller than 0. The area element of the apparent horizon is given by some quadratic expression, which is good because we expect it to be positive. And what one can do is to define the area element power spectrum. So we take essentially this object, Fourier transform it, and then average over angles. This quantity is such that if we now integrate over all momenta or over all values of n, if we analytically continue it to non-integer values, then we get the total area of the event horizon. This is kind of a useful quantity because it's very similar in spirit to the energy power spectrum. So here we have the energy density, which goes like v². We define the energy power spectrum to be this object, and it's very similar. If we just think of this sigma, the square root of the area element of the apparent horizon as a velocity, then we just naturally get this object, which is the area element power spectrum. And there are some earlier works which claim that the area element power spectrum is going to be related to the power spectrum for the energy density up to some factor of k². So if here we got k to the -5/3, we expect to get k to the -5/3 + 2. And in terms of a fit, we again get a fit that's within this value, at least as far as our statistics go, or maybe right at the boundary of it. I don't quite remember now. Okay, so this is our second result, which relates the area power spectrum to to the energy power spectrum. This is a geometric object. This is sort of a boundary object. So at least for the non-relativistic theory, it seems that one can relate a geometric quantity to this power law behavior. This is something that's been observed in decaying turbulence. So we sort of we didn't invent anything here, I should say. We're just showing that things seem to work in a relatively similar manner to the case where decaying turbulence was studied. Right now, you can see here that we don't have too many points in what's called the inertial range, the range where we have this k to the -5/3 behavior. And what needs to be done now is to try and interpret this result in terms of a more geometric quantity. Some ideas out there are fractal dimensions for the event horizon. And again, this is something that we want to do next.
Can I ask a question?
Yes.
Can you go back to that last slide?
I hope so. I managed to.
Great. So it looks like that k to the -5/3 + 2 scaling power looks suspiciously like the early time scaling of the energy on the right plot. Is it true?
You mean this here?
Yeah, it looks a lot like this.
I don't think it's related. I mean, this curve is associated with this time.
Oh, this, I see. Okay.
So this,
okay.
so I should have said it. The color
Okay.
coding is the same. So
Okay.
we're looking here at the latest time. I should have made a plot with other times, but this is the late time behavior of this power spectrum. So it should be compared to this expression. I agree that it looks similar, but I think that's kind of accidental.
Okay, I was just curious if the early time scaling is driven by the horizon, by this horizon average.
Spectrum. Yeah, no, I don't think it's related.
Okay, all right, thank you.
Okay. So this is what we've seen. We've seen that we can get driven turbulent behavior by placing the theory on a random metric. This, you might say this is expected or maybe not. When I talk to some of my colleagues who do fluid dynamics, they were kind of borderline about this. So I think this result in and of itself is one interesting result that we got. We're demonstrating that by placing our theory on a metric which fluctuates randomly, allows for turbulent behavior if the system is in initial thermal state. The second thing that I think is interesting here is that the area power spectrum seems to follow the energy power spectrum in the non-relativistic limit in the sense that I tried to describe. The obvious thing to do next is to try to increase the inertial range. See that we get a lot of resolution in the inertial range. We can go over 2 decades or so of momenta and still get this power law behavior. And I think once we have that, we'll really feel secure that what we're seeing is really turbulent behavior. For that, we're going to need large boxes and large grids. So that's some work. I talked about relativistic turbulence. I think this is an open question whether or not there's any sense of sensible definition of relativistic turbulence. And of course, what we really want, like I said at the very beginning, is to try and parameterize the energy power spectrum or higher moments of the average velocity field to some geometric quantity. So for example, one of the ideas out there is that the event horizon has in some sense a fractal dimension. Does the power spectrum relate to the fractal dimension of the event horizon? There are several papers out there. They all have different numbers for the fractal dimension. Some of them make sense, some of them don't. Once we have steady state turbulence, what we could do is just compute it very explicitly. Just, we have a manifold, which is the apparent horizon, and we can just compute its fractal dimension using an extension of standard methods to compute fractal dimensions of manifolds. Once we have that, and we can show that it's going to be related to the power spectrum or to velocity correlations, then we can start asking more theoretical questions. Is there a way to predict it? Can we get the -5/3 law from some property of the Einstein equations in black hole solutions? Okay, so this is for the future. I hope we'll be able to report on some of these issues soon. Thank you for listening.
Thank you very much, Amos, for a very clear and interesting talk. So, do we have questions?
So, so here is a question. So you mentioned the ensemble average and time average. So these two kinds of average are essentially the equivalent to each other, am I right?
Since it's a steady state, or well, it's an approximate steady state, then they're equivalent, yes.
Okay, I got it. So another question is, in your simulation, the apparent horizon is not fixed at a fixed coordinate time, right?
Well, this is a matter of how you. This is a coordinate dependent question. So in our coordinate system, the apparent horizon is not at the fixed value of rho.
Okay, I got it. Okay, thank you.
Other questions?
Yeah, hi. So very nice talk, very interesting. Yes, I have a question. So when you do hydrodynamics, I mean, by definition, you only have access to hydrodynamic modes, and you can only drive these modes. But when you do holography, you have the full theory. And now I could imagine it's a question of the scale at which you drive the system. You have this driving scale, KF. Does this play any role compared to, say, the scale set by quasi-normal modes or things like that?
Yeah, we didn't try to compare it to this. I mean, what we did was just, we weren't clever enough to try and compare it to quasi-normal modes. What we did was we just, tried some values by hand until we saw that we got a match to turbulent behavior. We didn't try and see whether, the energy momentum tensor can be written in terms of the constitutive relations of hydrodynamics. We didn't, try to fit hydrodynamics. We were really only looking for energy power spectrum. I agree that if you yank it too hard, the black hole is not going to behave hydrodynamically. It's going to do something very different. But we didn't really try that.
Yeah, and a related question is the definition of velocity. Of course, you have taken the Landau frame, but could you choose some different definition of velocity? I mean, you can add arbitrary higher derivative terms now, which would all, right?
Yeah. So again, I think there are works where they attempt to define relativistic turbulence, and what they do is they say, instead of looking at this energy power spectrum, what you can do is look at correlation functions, average of correlation functions of the energy momentum tensor in some limit. So in principle, instead of looking, and the way you derive these correlation functions of the energy momentum tensor is that you say, well, let's look at correlation functions of the energy momentum tensor such that if I take the non-relativistic limit and I'm in the Landau frame, then I'll get correlation functions, then I'll get the energy power spectrum or whatever correlation functions of the velocity field I want. So what we could have done instead of what we did was to look at correlation functions of the energy momentum tensor and see whether we get the right power spectrum or not. But since we're in such a non-relativistic limit, we're guaranteed to get what we got. So I think your question really is about relativistic turbulence. What do you do, when you cannot take the incompressible, when you don't have a limit or the limit where you have incompressible non-relativistic flow is not a good one. Then you run into all these questions that you're asking, and I don't have an answer to that. I don't know.
Okay, thank you. Thanks.
Can I maybe tag on to the question of the driving size of the driving force? And can you relate it to the temperature? Probably you said something like that, but the scale on which you drive the system.
Sorry, what's
can you relate the scale on which you drive the system? Can you relate that in any way? Because you showed that there's a peak in at KF at your driving force in some of the spectra that you had. And so what's
here,
that
for example?
Yeah, what's that KF in units of? Probably I missed it. So you show it in units of the ADS rate.
Well, right? Well, it's 21. It's at the n equals 21. So this is discrete, so it's n equals 21 out of 30. So n runs from minus 30 to 30, and kf is 21.
Ah, okay.
In units of n.
So is this what you would consider within the hydrodynamic regime? Because that's what Carl asked about, right? Is the driving force that you apply, is that within a hydrodynamic regime? Are you doing that slow enough?
No, I think the question is more about the amplitude. If the amplitude I think is too large, then you're going to be outside of hydrodynamics. Here, I guess you could drive it. Yeah, here I would say it's within hydrodynamics because you get the minus 5/3 law. Like I said, we didn't try to match it, but I would think it's more that the amplitude would drive you out of hydrodynamics rather than the driving force has this parameter d, which is the amplitude of the driving. I think the frequency is fine.
Okay. Yeah, I was just thinking very naively, trying to in my mind compare to the size of the frequency of a quasi-normal mode or the wavelength, which are all in the order of temperature. So that's all I.
I think it's the amplitude, because then you'd be going outside of the linearized regime, and then everything is going to break down.
Yeah, I see that.
But yeah, like I said, what we did was we tried to use a driving force that'll give us this minus 5/3 behavior, and this is what worked. And usually one takes the driving force to be a certain ratio of the box size, which is what we did, 0.6, I think. Sebastian is here; he probably knows better than I do.
Okay, thank you. I see René has a question.
Yeah. Hi, Amos.
Hi,
very nice talk. Hi. So you say there is nearly nothing known about relativistic turbulence. Is it possible to do something like an ultra-relativistic regime of some kind?
Yeah, that's a good question. I tried that for a little bit, but didn't manage to get very far. I think that's a good question. Probably should be pursued. It hasn't been done as far as I know.
Okay, thanks.
So in
Go ahead.
So in practice, how many times did you run your simulation to obtain your result?
How many runs did we do when we ensemble averaged?
Exactly.
36.
Okay, I see.
Matthias, I have a question. Can I ask?
Yeah, sure.
Oh, Amos, thank you very much for that very nice talk. My question is, most of the time we see that what is usually referred to as the regime of turbulence is where we find, for example, some power law behavior for the spectral function of energy. I would like to know, is it because we are not able to derive some precise results like 4/5 law of Kolmogorov, or the sufficient way to say that our system is turbulent is to derive such exact relations?
I'm not sure I understood the question. You're asking, so you're essentially asking, I think, about what I said at the very beginning. Is that
Yes.
is that
yes.
right? So I had this plot. This one, I think. Right. This is what you're asking about. Or the before this?
I think in none of your plot I saw my point. The prefactor 4/5 in the Kolmogorov relation, for example, for the 3-point function of velocity in positional space, an exact relation we know, for example, for the turbulence in 4 dimensions. My question is is it what we have to find in order to say that our system is turbulent, or finding some power law behavior for velocity or a spectral function velocity is sufficient to say that?
Well, I would say, well, I mean, I think this is an open question. So what I'm saying is, forget about holography and everything. In fluid dynamics, right now, apart from small n, nobody knows how to predict these powers. So now, if you have a turbulent behavior, what are you supposed to do? I mean, you can't predict it. So how do you know if it's turbulent or not? There's no crisp answers here. So for small n, things seem to work. So we say, for small n, Kolmogorov's theory is right. And then if for small n we get a behavior of this type, then we say it's turbulent. Now, for larger n, I would go with experiment and say, okay, if you can reproduce this blue curve via some theoretical construct, then I'd say you understand turbulence. Now, but again, since there's no theory behind it, I don't know if it's known how universal these results are. So, I don't know if you get some experiment and for n equals 8, you get some correlation function, which is right here. What does that mean? Is it turbulent? Is it not turbulent? I don't know.
Nice. Thank you.
I have a very quick question, hopefully. You showed that the T01 looks the same on all locations of rho.
Yes.
I think that was your plot on one of the slides.
Yes.
Do you expect that to change when you go to some sort introducing some domain wall solution like the people did in order to do the RG flow between two copies of a CFT? Would you imagine this to change?
So I can't say I really understand this. I mean, the warp factor can also, in principle, the warp factor could change as you go deeper into the bulk. It's only if it's sort of ADS throughout that it still goes like 1 over rho squared, or it's ADS to ADS. If the warp factor will change into some Lifshitz theory or what have you, then I think you'll get something different. But then you'd be asking about turbulent behavior, going from a theory which is, it's some extra going from a theory which has the Lorentz invariance in the UV and some other symmetry in the infrared would be interesting to study, but I think it's an extra complication. We don't even understand this properly. So that would be some extra complication that would be very interesting to see, but I don't know if it'll probably create more questions than answers.
I was just trying to understand why this is the same on the different at the different rows and like by breaking this.
It's completely clear why. It's an observation. I cannot prove it.
Okay. I jumped the line. I realized that Javi had a question, and I think then Blaise also had a question. Javi, did you raise your question? Are you still here? In case you are, I cannot hear you. I don't see him anymore. Okay, so then Blaise, please go ahead.
Hi, Amos.
Hi, Blaise.
Thanks for the talk. I was wondering, so you stressed again this mismatch between theory and experiment.
Yes.
Have you tried computing higher point functions? I mean, I realize that this is complicated, but it seems like this might be a way that holography could contribute something rather than just reproduce.
So no. In 2+1, so this is actually 3+1. In 2+1, as far as I understand, theory and experiment match better. And in the large D limit, this has been computed. And in a sort of in a large D limit where you take the number of dimensions to be very large, but you assume that only 2 dimensions, everything is uniform in all dimensions but 2. When you do that, you do get the n/3, which, as far as I understand, is something that's expected in 2+1 dimensions. So if you really want a holography to help, you'd have to run this in 3+1, which is challenging.
Numerically.
Numerically, yes.
Mm-hmm.
Yes. I mean, if we knew what bulk quantity we're supposed to look at in order to get this, that would be fantastic, because then maybe we wouldn't have to do it numerically. That would be solving the problem entirely. That would be great. For now, we're looking for threads, so we're just solving it numerically so we can see what exactly is going on. What's the quantity that we're supposed to look at?
Okay, thank you.
We had already a few questions, but are there, like, we should maybe let Amos go, but what time, like, is there any other questions?
I can stay for questions.
Okay, good. Maybe we can also have some informal questions after the recording stop, but is there anything urgent right now? Because then I'll stop the recording. And like, first of all, thank everyone officially.
Thank you.
Especially Amos for giving his talk.